ఓకేనా? హలో, హలో, కాలేదా?
It's good. No, wait. Yeah. Okay, so good morning. Yesterday we talked about the assignment. So we had 3 more theoretical exercises. And regarding the MATLAB assignment, okay, so you see you have a link. Just like I said, if you go to my website and you go to publications, books, you can download the MATLAB figures. If anybody had some problems, just let me know. You can download the MATLAB figures. And then in this zip file, you have all the MATLAB codes. Each one generates by its name, the name of the code. It corresponds to a figure in the book. So I will share with you also the material, but here in the example that I showed before, figures 2 to 5, these are figures 2 to 5. You see, this is figure 2, 3, 4, 5. These figures, they correspond to figures 2.2 to 2.5. So when you download these zip files, you open figure 2.2, the MATLAB code for figure 2.2, you will get this figure. Okay, and so on. So you can open the code, you can look at it, you can change parameters, and so on. So you're supposed to return the assignment tomorrow. If you need more time, it's okay, no rush. If another day, it's also okay, okay? But try to do it because it will help you to understand the material. And also, a good thing, at least with the MATLAB assignments, each one can work alone to think about, play with parameters, change parameters, so on, and then try to jointly with other people to discuss, because everybody will do something else. Discuss what you did, what the other one, what he did, he or she, why are the results like this. You can make changes and try to discuss with each other, okay? This is helpful. Any questions or any problems with the assignments? Any questions? Okay. So yesterday we talked regarding the quiz. There will be some questions. It's not closed. It's like a close. You just need to choose answer from a few options. It will be just based on understanding. So you don't need to open the material. Without any material, just to understand. It will not include derivations that you need to find mathematically. It's just to see the understanding. It's more actually for us to see the understanding in the course, okay? So if you read the slides, you understand what I talked yesterday and today. It should be easy, okay? Yesterday I talked about Wiener filter, okay? So do we have here one? Okay. So single channel signal enhancement using Wiener filter. One is enough. Okay, thank you. So the problem was that we have some measurement, a signal, yt. T is discrete. And we know that our model contains a signal, desired signal, plus noise. And we know that the signal and the noise are uncorrelated. We can say even statistically independent, but for us here, for the Wiener filter, it's enough that they are uncorrelated. And then we wanted to find an estimate of the sample. Zt is an estimate of the sample on time t using L samples, L past samples of y. So we obtain it as H transform y. And y is a vector that contains L past samples of these signals. So this is a causal estimation. And we talked about differences between estimation, prediction, causal, non-causal, and so on. So for Wiener filter, if we want to find the filter here, we need to find the mean squared error, which means that if we take Zt minus Xt, and we take, this is the error, and we take the squared error, and we take the mean of this squared error. So we call that JH, which is the mean squared error. And in order to find an optimal filter, an optimal Wiener filter, we need to express this mean squared error as a function of H. This is what we did. And then we found H that minimizes over all H. Okay, so if I need more space here, okay, so we minimize this JH, the mean squared error, over all possible H. And the filter that finds this minimum, we call it H Wiener. And if we use this filter, the Wiener filter, so JH Wiener, this is the minimum mean squared error, the minimum mean squared error that can be achieved for this problem. And we saw different expressions for the Wiener filter based on information. And the information that we need is actually the correlation matrices, Rx and Rv. And we took that these matrices are the size L by L samples. So we have L by L samples. And it actually contains that the correlation between any samples inside the vector X. So if we take vector X of L samples, we know the correlation, the average. Okay, so it's a correlation between any two samples. And this information is very important, and it's not easy to get in practice. So there are different methods. Okay, any questions on that? Now, let's continue. So we saw that we can write the mean squared error as a superposition of two terms. First term, we call it JD, which is relevant. It comes from the distortion of the signal, plus J, we can call it residual noise or something like that. We call it N, it can Rn or whatever. It doesn't really matter, but these two terms we can either try to minimize their summation, or we can try to do different things. Okay? So this comes from the residual noise. Why? Because if we write this, so we can write it as the expectation of Z, which is H transpose X plus H transpose V minus XT. So you see that we have two terms here. We can write it as, let's write it over here, expectation of H transpose X minus XT plus expectation of H transpose V. Okay. So what we try to achieve with the Wiener filter is actually to minimize the sum of these two components. But sometimes we want to have undistorted signal. Maybe we want to put more emphasis to this part because the distortion is more important. Maybe we want to give more emphasis on this part. So we want to reduce more noise. So we have a trade-off. We have a trade-off how much noise we reduce. What is this part? And what is this part? So instead of minimizing this sum, the mean squared error, we can try to minimize summation like this. And we will call it, for example, J mu H. Okay, so we have a parameter mu. Now, mu is larger than 0. Positive number. So if mu, this parameter, is larger than 1, it means that we give more emphasis to this part compared to this part. So if mu is larger than 1, it means that we want to reduce, this part is more important because we put here a more weight. So what will happen if we found here, if we find H, let's call it H mu, okay? And we can say H mu trade-off. We can call it something like that. This is the trade-off parameter with a parameter mu. And this will be the filter that minimizes over H, J mu H. So we know that for mu equals to 1, H, we can put the T. This will be the trade-off. Let's say that just a notation. So we call it trade-off with a parameter mu. So actually, it doesn't really matter how you denote things, but this will be the trade-off filter with a parameter mu. So for mu equals to 1, it will be equal, so if I put here 1, it will be equal to the Wiener filter. course. But if I take mu larger than 1, what will happen? This filter will result in more noise reduction because we give more weight to this part. So it will result in more higher noise reduction because we want, if this is large, so we want to make this smaller by making this smaller, even further compared to the winner. So it will come on the account of this part. This part will be larger. So mu larger than 1 will result more noise reduction, but also more distortion. Okay? So let's say that GIAN H T mu will go, if this is large, it has to go down. But at the expense that JD HT mu will go up when we try to minimize this. And vice versa, if mu is smaller than 1, we will get, if it's smaller than 1, so we put less emphasis. This part is less important, so JN will increase, which means that this filter will reduce less noise. So if we reduce less noise, if we make mu smaller than 1, means that this part is less important, so there is more importance, relative importance to this part. So JD, the distortion, you see this is the distortion, will, the mean squared error for the distortion, it will go down. That's why we call it a trade-off filter. So you see that this parameter, actually, we can interpret that parameter as a Lagrange multiplier. Because this mu can be regarded as a solution to an optimization problem like this. So we can write the optimization problem like this. Suppose that we want to minimize JDH subject to NH equals to some value. Okay, so we can say JNH, I deleted that, but it's, suppose that I give here a certain value. Let's say Aleph sigma V squared, for example, or something else, whatever. Okay, but suppose that I want to restrict this value to a certain value, which means that how much noise I want to suppress. So I limit that, how much noise I want to suppress, and then subject to such a constraint, I would like to minimize this. So this will be using a Lagrange multiplier. I can use a Lagrange multiplier mu, and it will be equivalent to this problem. But here I can change mu such that the constraint is satisfied. But if I don't care about this constraint, I can choose any value of mu. If I want that this will be equivalent to this problem, I need to change mu until some constraint is satisfied. This is the only difference. Okay, so let's see it here. So this is the trade-off filter. And it's very important in practice to have some trade-off between noise reduction and distortion. Okay? Because the Wiener filter tries to minimize the total mean squared error, which sometimes we don't want that. We want to control how much distortion and how much noise reduction, because it's a kind of trade-off. And sometimes it's subjective. For some people, they want less distortion. Some people, they want more noise reduction because they don't want to noise. But this is a trade-off. And in some devices, you can also change the amount of noise reduction. And if you try to reduce more noise, you know that it results in higher distortion generally. Okay? So it comes at the cost. So we can find this problem, something like this. Okay? Minimizing the distortion based mean squared error subject to some constraint. And then using Lagrange multiplier, we can write it like this. You see, this is like we can remove this because it's constant. This is independent of h, so we can remove this. And then we try to trade-off filter. What is this vector that minimizes this sum, where mu is any parameter that is larger than 0. And we now understand also what is the effect of taking mu larger than 1 or mu smaller than 1. If mu is 1, then we get the Wiener filter. But if this is our objective, to get GIAN, which is the noise reduction or the noise, residual noise based mean squared error, then we need to find, maybe numerically, maybe by explicit expression, it doesn't really matter. But then we need to find the exact mu such that this constraint or requirement will be satisfied. Okay, very simple. So what do you think? How the solution to this problem looks like? If I go here, what will be the solution? What do I need to do? I take derivative of this with respect to h and equate it to 0, just like what we did for the Wiener filter. Actually, you can take the Wiener filter and instead of putting instead of having GIAN, we will get mu multiplied with this part. So actually, it's just like multiplying RV. If we multiply RV with mu, we get the trade-off instead of the Wiener. Okay? But don't try to guess. It's more intuitive. Yeah, I mean, it makes sense that if you multiply RV with mu, then you give more emphasis to this part. And actually, if we find if we have exactly the expression for J, and we put mu, you will see that here we have mu H transpose RV H. So when we put mu, it's just like multiplying RV. It's the same. Okay? Do you see that? Maybe I will write it. I don't want to go to the solution yet, but let me go back to the of JD and JN. Okay? Even though it's very easy to find So I write this scalar differently. One here, one here. But it's the same scalar, because the scalar transpose is the same. But here I can put the expectation into the inner side. So I get H transpose RVH. So if I multiply this with mu, it's the same as multiply RV with, and then with the solution. So you need to do the derivative and equate it to 0 again. Of course, you can do that. But if you know the solution for the Wiener filter, you know immediately the solution for the Trade-off filter. And you get the solution. That's why you see that the solution becomes like this. See, the same solution, but we replace instead of RV, we put mu RV. And by the way, all the expressions that we saw before, okay? But you need to be careful, because if you have another expression like here, in this expression, this is solution. But if you change equals, if you take a different expression, you take Rx now. And instead of Rx, you will replace it with Ry minus Rv. You don't multiply RV with mu, because it's not true. So you need only to take the solution. Okay, so we can get different expressions and so on. Now we can keep this filter with the parameter mu and take mu larger than 1, 1 or smaller than 1. And we know what does mu, how does it influence the mean squared error, or the solution and noise reduction, the trade-off between noise reduction and distortion. Alternatively, we can change mu such that the constraint here, the constraint will be satisfied, which is the same as the noise reduction factor. Noise reduction factor is equal to 1 over aleph. Okay? So we can choose mu such that this constraint will be satisfied. Okay, so it's up to you. I would like to go to an example, but before I go to an example, any questions so far? Okay, so I will go and show an example. But before that, you have this, what we talked before. And also we have this property that we talked about, that the Wiener filter, with the Wiener filter, the output SNR is always larger than the input SNR, even though we didn't talk about SNR. So this is true for any parameter mu which is larger than 0. With any trade-off filter, the output SNR will be always larger or equal to the input SNR, which is also something nice to have. Because we didn't work, we just worked about minimizing. By the way, it depends on the model. Okay? So for this model that y equals to x plus v, and obtaining the trade-off filter, we have this result. But it's not so obvious. Okay? You need to check and prove it. So the proof is here. Okay, so you have here the proof. But it's nice to know that the output SNR is increasing, even for any trade-off filter with any parameter mu. Now let's talk about an example. An example, it will make things even clearer. Suppose that we have a signal x, and we don't know too much information about the signal. We just know what is the correlation between any two samples of x. So the correlation between two samples of x goes or decays by this distance. And alpha can be any number between 1 and minus 1. Okay, so we have the correlation. So if the distance between the samples is large, we see that the correlation can be, it will become smaller. And also we see that alpha can be negative. What does it mean, negative? If alpha is negative, what does it mean that the correlation between two samples is negative? So yes, so it changed sign. So correlation can be with the same sign or change the sign. It means that if two samples have similar values, so if we know one, we know that the other one is close to that. Or it's in the other sign, so it will be negative. By the way, if alpha, question, if alpha is 1, okay. Okay, so it means that the two samples, if you know one sample and the correlation is 1, okay, so it's 1, and t minus t can be any number, so it will be 1. Okay, so all the samples, you say that they perfectly correlate. Okay, and if it's minus, so minus 1, so it depends if it's the next sample or even if this distance is even or odd. So it changes sign from sample to sample. Okay, but this is but the correlation decays. And suppose that this kind of signal, we add some noise, white Gaussian noise. In the assignment, you can add different types of noise, also whatever you like, okay? But here it's simple. And then we have the measurements of the signal. So the input SNR, you see the input SNR, we can compute it like this. RV, the correlation matrix. The correlation matrix for the noise is sigma v squared multiplied with identity matrix, L by L identity matrix, because it's white noise with the variance sigma v. And the correlation for the desired signal from this model looks like this. So it's alpha, and this is the difference between samples. So along the diagonal, what it will be? Along the diagonal? Along the diagonal, it's 1, right? Because it's alpha to the power of 0. So along the diagonal is 1. So Rx looks like that. It's L by L matrix. Here we have 1s. And here we have alpha, and so on. Here we have alpha squared, and so on, alpha to the third, and so on. So you see, when you have two samples with larger distance, the correlation decays. By the way, there is a name for this kind of matrices. Okay? Okay, so I want to note that here, if we use Rx, if we use this matrix, we assume we know alpha. Actually, is it difficult? Compared to the previous example number 1 that we talked yesterday, over there we assumed it was a cosine signal, and we assumed for the purpose of constructing the matrix Rx, we assumed that we know the amplitude, A, and also the frequency, F0, which is a lot of information. We need to estimate them. Here, we only assume that we know that the correlate. We assume a few things. We know the correlation coefficient, like this. We know alpha. And we also know this model, that the correlation looks like this. Okay? But if you want to estimate Rx from the data, of course, it will contain some errors. Even here, even if you know that this, you need to estimate alpha. And if you estimate that from fixed length of measurements, especially noisy measurements, probably you will not have the correct alpha. And then you can ask yourself, okay, what is the effect of incorrect alpha? How does it affect the filter? How does it affect the performance? What is the performance criterion here? We have a few performance criteria. First, we have the mean squared error. And we can have also here the weighted mean squared error. But we can ask ourselves, how does it affect the gain in SNR, the desired signal, the reduction factor, the noise reduction factor, the distortion, all the performance measures that we talked before. We can ask ourselves how inaccurate estimate of alpha, this error in alpha, how does it affect the performance measures that we talked before? This is a good question, and you need to find how does it affect for this different type of signals. Okay, so let's continue. So we can find the trade-off filter from the previous equation, and we can also find mu that satisfies this constraint for different values of aleph. Okay, so first let's assume that we have a certain example. So alpha, suppose that it's 0.8. We have a filter length of L equals to 30, which means that to find an estimate Z, we look for the past 30 samples of the signal, and we can take several values of aleph, how much noise we want to reduce. Okay? So let's see this example. This plot. This is the gain in SNR. These are some performance measures. The gain in SNR, the mean squared error. You see, we check the mean squared error, not the weighted mean squared error. Here is the noise reduction factor, and this is the desired signal reduction factor. So we have 4 lines, 4 plots here, and for different values of aleph. Aleph equals to minus 12 dB, this is the blue, and minus 13 dB, minus 14 dB, the red, and minus 15 dB. So first we see that for different values of aleph, we have the noise reduction factor is constant as a function of input SNR. Of course, because this was our constraint. We chose mu such that the noise reduction factor will be minus aleph. Okay, we wrote it before. Okay, it's here. It's here, this constraint. If we, GIAN, this is the mean squared error relative to, based on the noise reduction. So writing this is the same as a constraint that the noise reduction factor will be 1 over aleph, which in dB, it means that the noise reduction factor in dB is minus aleph. That's why we have in this example, we have it here, that the noise reduction factor is constant and equals to minus aleph. So if we increased, or if we want to, aleph becomes lower, so we increase the noise reduction, okay? You see, we have more noise reduction. Aleph lower, it means that we want to reduce more noise. So aleph is lower, see blue, green, red, cyan. So we increase the noise reduction. If we increase the noise reduction, we also get higher output SNR. So the gain in SNR also increases. But we pay for that. What happens to the desired signal reduction factor? Also it increases. Okay, and also the mean squared error increases, which means that if we want to reduce more noise, the distortion will be higher. We'll get higher distortion. We see it from here. The distortion is higher. The mean squared error, you see, when you reduce more noise, you expect, so we have two terms. You reduce more noise. So this part will be smaller. But we get that the mean squared error becomes larger. Okay? So what do you say? What can we say about that? That this becomes smaller, but the total becomes even larger. So this becomes even larger compared to the reduction in the noise. Okay, so the summation of this part, the summation, this is the MSE, the summation of the noise reduction based MSE and the distortion based MSE, both of them increase, which means that this increases more than this decreases using the trade-off. On this example, I didn't prove that it's always true, okay? But for this example, you see that even though we increase the noise reduction, we have less noise, the total MSE increases, which means that the distortion increases at a rate higher than the rate of decreasing the noise. It has more effect, okay? Okay, questions on this example? Okay, let's move on. Let's talk about the MVDR filter. Okay, so what is the MVDR filter? We can define it that we want to have distortionless response. So we want this to be 0. With the trade-off filter, no matter what is mu, if you choose mu, you increase it as much as you want. Still, this JD, which means that the signal-based distortion, MSE, it will not go to 0. But suppose that we want this to be 0. So our problem is that we can define the problem or formulate the problem that we want to have 0 distortion. So this will be 0. And then we like to minimize JN. So it's not spatial case or particular case with a certain mu of the trade-off filter. It's another problem, okay? So this is the MVDR filter. And the question is, before I continue, think about intuitively the MVDR filter. If we like the distortion to be 0, and then we try to minimize only this part, compared to the trade-off filter, which filter reduces more noise? The trade-off filter or the MVDR? I hear MVDR and trade-off. Okay? Let's think about it. Which one requires that the distortion will be smaller? MVDR or trade-off? MVDR. Okay, so the distortion is smaller. If the distortion is smaller, what does it mean about noise reduction? less noise reduction because you have a constraint. You cannot get the more noise reduction that you want, it will cost you that it will increase the distortion. You want to reduce more noise, the distortion will increase. It comes together. So if you require that the distortion will be 0, we have a limit how much noise we can reduce. Okay? And this is a nice thing. So first we have a comparison between Wiener filter, between trade-off filter, and between MVDR, even without deriving the MVDR. Okay? So if we compare we can remove here. Okay. So if we compare the noise reduction factor, Cn for H Wiener compared to noise reduction factor with a trade-off filter compared to noise reduction factor with HMVDR. Okay? Which one will reduce? Which one will be the highest? Highest, it means that we reduce more noise. Which one? Okay, so suppose that we try to suppress noise with a certain signal, and the signal is band limited. Suppose that we sample the signal with 16 kilohertz, and we know that the desired signal is contained in a certain bandwidth, maybe from 1 to 2 kilohertz. What? If the desired signal, exactly what you say. If the desired signal is, we know that it's contained within a certain bandwidth from 1 to 2 kilohertz, we can remove all the low frequencies up to 1 kilohertz and remove all the noise higher than 2 kilohertz, and we get noise reduction without any distortion. This is exactly the MVDR, what it tries to do. It tries to find the signal subspace. The signal subspace in this example is between 1 to 2 kilohertz. And then in this subspace, we don't touch, we don't do anything. We keep it as is. And in the noise subspace, which is up to 1 kilohertz, and from 2 up, higher than 2 kilohertz, we suppress all the noise. Okay. So if we compare it to Wiener filter, the Wiener filter, of course, it will remove all the noise in the noise subspace up to 1 kilohertz, and above 2 kilohertz it will remove, just like the MVDR. But what will it do in the signal subspace from 1 to 2 kilohertz? It will also decrease some noise, but introduce some distortion based on the signal-to-noise ratio. Depends if we have more signal or more noise, because it tries to minimize the mean squared error. The trade-off is very similar to the Wiener filter. It just gives different weight with a parameter mu to the noise, to the signal-to-noise ratio in that signal subspace. Now my question is, do we have to do it in the Fourier transform? Or we do it, what is the signal subspace? Sometimes we call it, instead of signal subspace, signal plus noise subspace. But the noise we assume that is full rank. It's all over. So we say the signal subspace, it contains some noise. And the noise subspace, it's without any signal, desired signal. And then we want to find what is the signal subspace, what is the noise subspace, and then the Wiener will remove, the MVDR will remove only the noise in the noise-only subspace, while the other filters, the Wiener, for example, it will remove the noise in the noise subspace, but also it will distort the signal to achieve more noise reduction. And the trade-off also will trade off how much in the signal subspace we want to remove more noise compared to distortion. This is the intuition behind it, okay? Any questions? Okay, so we will have 10 minutes break. Now it's 10 minutes after 10. 10 minutes break. We will return at 10:20. We will continue from here. Think about questions if you have immediately after the break, because I want people to ask questions, okay? If everything is clear, it's okay. If something is not clear, you have some thoughts, it's good everybody to share with others. Matrix, and then we find the eigenvectors and eigenvalues. So the matrix Qx, we can diagonalize the matrix Rx. So if we diagonalize this matrix Rx, using eigenvectors and eigenvalues. The columns in the matrix QX are the eigenvectors, and the diagonal along in the matrix lambda x contains the eigenvalues. So if we know that the rank of Rx is lower than L, so the rank is P, which is lower than L, we know that some of the eigenvalues here in lambda are 0. So we have P non-zero eigenvalues. So what we need to know, we can take this matrix and order the eigenvectors according to decreasing order of the eigenvalues. And we know that any signal, any vector, actually any vector, y or x or v, any vector of length L, we can write it as a superposition of these vectors. Why? Because these vectors span all vectors of length L. They span the whole space. But if the rank of Rx is only P, which is smaller than L, it means that we can take only P eigenvectors, and these P eigenvectors with the eigenvalues which are different than 0 span the signal subspace. So while any signal, y for example, vector y, and for anything, actually any vector, any general vector of length L can be written as a superposition from I equals to 1 to L outside, like this. Okay, thank you. Okay, so I hope that you could hear what I said before, or maybe I need to repeat. Okay, okay. So what will be the coefficient? It's a superposition of these vectors. What is the coefficient here? Exactly, exactly. So it's y transpose q x I. Okay, so these are coefficients. These are numbers. So these numbers multiply with it. But if we take a vector of the desired signal, so we know that a vector of the desired signal, we don't need all these vectors. It's sufficient to take only the vectors that correspond to eigenvalues which are larger than 0 or different than 0. So we have here I from 1 to p q x I x t transpose q x I. Okay, these are the coefficients. Okay, and we know that actually this inner product, we know but yesterday they replaced the batteries, no? Or maybe day before yesterday. Okay, I don't know why it turns off. Anyway, so that's why the signal subspace is spanned by the first eigenvectors, the first p eigenvectors that correspond to eigenvalues which are different than 0. What about the eigenvalues? What do you think? Can we? It shows like the battery is empty. Yeah, it shows the battery level. Shows like it's empty. Okay, because the video needs a microphone. We'll wait a few minutes. So it turns off. To take something from your background. Some people have background in radar, some sonar, some signal processing, and so on. So think about single channel signal enhancement. Suppose that you are noisy measurement of the signal, and you want to enhance the
to estimate the desired signal that is contained. So we assume certain models in the example, in that panel. Try to take something for your research, or if you don't have something relevant, try to think about, you can read in the literature, okay, about something relevant. Signal announcement, you don't know about it. And I don't have to read like journal papers for publicity, but just to think about the problem, how the problem is formulated, and how does it compare to what we achieved, what do we have since we studied in single compositional enhancement. How can we use what we studied and what is missing? Because I gave you some insight, what is missing. For example, in the example that we saw here, we need our x and our y, or our x and our b, which is not easy. So just think, even without solving the problem, think about how the real problem in practice can be addressed or formulated, what is missing, what people need additional information, and so on. If you don't have something relevant to your research, think about radar. We talked about radar, sonar. If you like technology, also interesting, the more difficult underwater signals, propagation, and so on. Read about anything that interests you, that is related to signal enhancement, and see how the problem is formulated. Okay? Try to understand the problem from the different disciplines. And if you like, some of you, okay, prepare one slide or two slides, whatever. Talk about this problem in front of the class. Okay? Then you know you will have really good fun. This can be relevant to signal enhancement in the time domain. You will study also in the frequency domain or multi-channel, whatever you like. Okay? It will be nice. And then you can give some time to people to talk in front of the class about this problem that's interesting. We're waiting for the batteries, and you can check. Do you have questions? Yeah, it's always true. You know, there's no full answer these days. When you try to achieve something, it comes at the cost of others. And so if you take different methods, usually any method that you choose to signal enhancement, you combine some trade-offs. So sometimes the trade-offs come between noise reduction and signal distortion. Sometimes it requires more computational complexity, sometimes more memory. For example, using deep learning. Oh, it works.
Okay, thank you. Maybe we need... Okay, you need to define a model. Model, it means what is the size of the model, what is the layers, the parameters, model better, but then what you pay, you need more training data, a larger data, and so on. So everything comes with here we see a thin trade-off. How much noise you reduce, what is the distortion? If you
come at a cost. Okay?
This in R.
So yes. And when you reduce so you pay for that.
Between our Okay. More questions? Did you want to ask something? Or? Okay. Okay. So this is the signal subspace. The signal subspace, it means that any vector of x, any vector of L of x is spanned, can be written as a superposition of the first eigenvectors, or these eigenvectors that correspond to 0, which
between p plus 1 to L, what happens with those coefficients? Coefficients from p plus 1 to L. So this contribution will be only noise. Okay? Do you see the equivalence between signal subspace? So, and Fourier transform. So suppose that we transform the signal into the Fourier transform. So think about that these coefficients, this is the span, this is the frequency band that contains the signal. So outside this frequency band, this signal subspace, we have only noise. So what we do with Y, we span it into all these eigenvectors, and we choose only the eigenvalues between 1 to p. The other, if we take z, which is an estimate of xt, we will estimate it only based on the first p eigenvector. Okay? Only for
so we will
we don't touch it from 1 to p, and then we agree that we will not have distortion, even though we remove all the coefficients, all the contributions from the noise subspace. It's just like removing the substance that contains only noise from p plus 1 to L. Okay? So if we can see the mathematics behind it. So now the mathematics will become much more clear.
have only p eigenvalues which are larger than 0, strictly positive. And also, we know that this matrix is orthogonal. You see? So QT transpose. So we know that eigenvectors of a symmetric matrix are orthogonal. have this property. And as I said, these are the eigenvalues. And we know that the first P eigenvalues are less than 0. So we can split the signal subspace, the old subspace of vectors of length L, into two subspaces. One subspace is spanned by the first P eigenvectors here, and the others from P plus 1 to L. Okay. Question. Okay, ready for a question? If P is smaller, can we reduce more noise or less noise? What is the effect of P? What? Exactly. So if P is smaller, it means that the noise-only subspace is larger. So we have more noise to reduce without any distortion. So with the MVDR, we will see that if P is smaller, it means that the signal is contained in a smaller subspace. We can reduce more noise without distorting the signal. What? If P is L. Good question. If P is L, what does it mean? That the MVDR, what will happen with MVDR? No noise reduction. It doesn't do anything. Actually, Z will be equal to Y. No noise reduction. Why? Because the constraint is no distortion of the signal. And if P equals to L, we don't have any noise to reduce without distorting the signal. If what? With Wiener filter, yes, but the Wiener filter introduces distortion. So if you allow distortion, you can always reduce noise. And with the trade-off, you have a trade-off. If it reduces more noise than Wiener or less. And this will come how much distortion you introduce. Okay? But the MVDR, it doesn't allow any distortion. That's why we need some subspace of noise only. It's just like with the Fourier transform, if the signal is present in all frequencies, then you cannot reduce noise. Okay? But I will give you also some interesting thought. When we say about here, we talk about signal, and maybe the signal is stationary or not. But if the signal is not stationary, it means that, suppose that, for example, speech signal, if you take the Fourier transform of a long speech signal, long it can be a few seconds of speech, you will identify that the signal is present in all frequencies. Okay? So then you think, okay, then MVDR will not be able to reduce any noise. Yes? So MVDR filter will not be able to reduce any noise. That's why we need other filters that put some trade-off between noise reduction and distortion. So I say, I can tell you that even MVDR, single channel speech enhancement, can reduce noise. What do you think? How this can happen? How can MVDR reduce noise even for speech signal that is contained in all frequencies? What do you think? No, I said single channel. Multi-channel, we come to that. I agree with you. Multi-channel, we have more possibilities. But even single channel, it can reduce noise. What? Exactly. Okay, by windowing. So, actually, I wanted two answers. Okay? Windowing, that's a good... okay, Okay, because you started with this, I will talk about this, this solution, windowing. Okay, so if we window the speech signal to intervals by windows, intervals of a few tens of milliseconds, 20 milliseconds, 30 milliseconds, 50 milliseconds. During this interval, we have just a small portion of the speech phoneme, or some part of the speech signal. And in that part, it doesn't span all frequencies. So you can see that the speech signal is contained in some of the frequencies. So we can remove this noise in other frequency without any distortion. And then for each window, we can remove noise from other frequencies. This is one thing. Okay? So it's a very good answer by windowing. Do you think about other thing? Not speech, or any signal. Suppose that the signal is contained in all frequencies, and I use MVDR. Still, I can remove some of the noise. How? For stationary signal, not speech, any signal. Signal that contains all frequencies. And still, I can remove noise without any distortion. How can that happen? Okay, so it's, if we think about it, I didn't say that we need to implement MVDR in the Fourier transform. So maybe it contains all frequencies. But maybe the eigenvectors, the first eigenvectors, so if I find the eigenvectors and eigenvalues, I see that the rank of Rx is P, which is lower than L, even though it contains all the frequencies. You see, the eigenvectors, even lower rank than L, low rank of Rx, maybe the signal is contained in all frequencies, but when I span it using the eigenvectors, I need only P eigenvectors. Okay? Do you know how we call this transform? This is very useful for signal processing. Many times for images and so on and other signals. So this is called Karhunen-Loew transform. Okay? If you're not familiar, you can read about it. Karhunen-Loew transform. Which means that instead of Fourier transform, which you are familiar, we transform the signal. This is the transform of the signal, or representation of the signal using the Karhunen-Loew transform, using the eigenvectors of the correlation matrix. Okay? So even though the signal is contained in all frequency using the Fourier transform, it doesn't mean that is lower rank or can be represented by a smaller number of eigenvectors using the Karhunen-Loew transform. Because here we use the Karhunen-Loew transform. Okay, so in the Fourier transform, maybe it's full rank, like or it's not full rank, or maybe we need all the frequencies. We need to go from I to L, even here, from I to L, using not the eigenvectors of the correlation matrix of X, but if we use the space, okay, the vector subspace of the Fourier transform. So if we take the Fourier matrix, the Fourier transform matrix, L by L, and we take the columns of the Fourier transform matrix, so maybe we need all the vectors to represent a signal of X. That's why we move to the Karhunen-Loew, because here it depends on the rank. Okay, if something is unfamiliar or you want to ask questions, please ask questions. Okay? Okay. Any questions? Okay, so let's continue. So we split this matrix into two parts, the signal subspace, which is sometimes we call it signal plus noise, and with to the null subspace. Sometimes we call it null subspace or noise subspace. Null subspace, it means that there is no signal over there. Noise subspace. Okay, so these terms are equivalent, are the same terms. So this matrix, the size is L by P, and this matrix is L by L minus P. So actually we can write, you see, we can write any vector of size of length L of X. We can use, instead of the full matrix, full representation of the signal, we can use only the first P eigenvectors. It's the same, because outside that, we don't have any signal. Okay? So we say, what is the distortionless constraint? Because what we need to do with the MVDR, we minimize the noise at the output. This is the estimate. We want here that to minimize the noise, because it contains noise plus filter desired. So we want to minimize the noise while not distorting the desired signal. So we can write the distortionless constraint in such a way that H transpose, this is the distortionless constraint. H transpose X equals to X, right? This is the distortionless. Why? Because how do we obtain this? We obtained it as H transpose Y. And this contains two parts. H transpose X plus H transpose V. So we want to minimize the variance of this. So the variance of the residual noise. But we want that this will be equal exactly to xt, which means, this means that the filtered desired part in the estimate is not distorted. And this is the residual noise. Okay? And we want to minimize this. So what is the constraint? That H transpose X equals to X. So it's equivalent to say that H transpose, that we apply H transpose to any Q xi from I to P remains the same. It's the same. See? So it will be like if you take H transpose that we apply it to the matrix Qx prime. Qx prime contains only the first P eigenvectors. Okay? So it's just like taking the vector. This is vector 1 and all zeros. Okay? You take it like this. So it's the same as taking I and 1 and all zeros, and you apply it to the same matrix. So let's think about this vector, okay? So how many constraints do we have here? Here, in the equation 62. How many constraints? How many equations? This is a vector, right? What is the length of this vector? What? What is the size of this vector? No, not L, P, P, okay? If it was L, it was not good. Then, because if we take subspace of, if we take any subspace with L, with a basis of L vectors, and we apply HT to all these L vectors, and we want them to be distortionless, then it means that we cannot reduce any noise. Here, instead of applying it to any x, any signal x, we apply it only to P eigenvectors. Okay? If I write it here in a matrix form, actually we have P equations. P equations, it means that if we apply H to any eigenvector from 1 to P, the first eigenvector, to any eigenvectors from I to P, we apply it, so it's distortionless, remains the same. Okay? You see, this equation 62 is just like writing that H transpose Q xi equals to Q xi for all I equals 1 to P. So here we have P constraints. The constraint is on the signal subspace, and the signal subspace is spanned by Q eigenvectors. So using these constraints. So instead of saying that H transpose X is equal to X to any X, any possible X, we need to apply it for all eigenvectors from 1 to L if we don't know the rank of X, the signal subspace. So just like the Fourier transform, so you take the representation of the Fourier matrix, Fourier transform matrix. So it will be any L vectors that span any vector of length L. But then it's enough that we have only P constraints, which is less than L. That's why we can suppress some noise. Okay? So our problem of the MVDR, you see, this is a very nice problem. To minimize the variance of the noise, to minimize this part, the variance of this part. Subject to P constraints. These are P constraints. And so if we don't want to have any distortion in this signal subspace, we can remove it. So we have this solution, okay, like this. So actually, we can check if this constraint is satisfied using this solution. This is the first thing to do. When you see a solution, first try to find the solution to prove that it's like this. But also, we can check that if we take this constraint, if this solution is satisfied, we can put HMVDR here and to see if this is satisfied, which is very easy to see. Okay? Take the transpose here and multiply it with QX prime transpose from here. So this cancels, and then you get exactly this. Straightforward to see. But also, what it means, you need to understand what it means. That in this signal subspace, the filter doesn't do anything. So all the coefficients which are represented, all the part of the signal that is represented in the first from 1 to P, we don't do anything with the filter H. It doesn't touch them. it keeps them intact, like this. And then it reduces the noise in the remaining subspace. So it actually, the easiest way to reduce the noise is to put nulls, zeros, in the other coefficients. Very easy. Okay, let's continue. So we see that the MVDR can also be expressed differently, which is very nice, because if we compare this solution, you see this solution, we see Qx. By the way, to find, we assume that we know information. What kind of information we know? Still here, we know the information Rx. You see? So along all this single channel signal enhancement, we assume that we know Rx and Rv. That's why we know the eigenvectors that diagonalize Rx. Okay. And instead of using Rv and Rx, we can change it using Ry and Rx. So it's Ry and Rx, the eigenvectors are from here. So instead of using Rv, which we need to estimate it based on the noise, here in this expression, we see that once we know the eigenvectors that diagonalize Rx, here, if we use something adaptive, for example, we use the correlation matrix of the measurements, because sometimes it's easier to find the correlation matrix of the measurements based on received data. By the way, if we don't know the eigenvectors of Rx, just like what you said before, okay? Because it's very difficult to find for each interval of window the Rx, and then to find the eigenvectors that diagonalize this part of the signal. Think about it. Suppose that I have non-stationary signal like speech. For each interval of a few tenths of milliseconds, I need to find Rx, and then I need to find the matrix Q, the eigenvectors that diagonalize Rx and that window, and then I need to represent the signal and then remove the null subspace and so on, which is difficult. It's time-consuming, high computational complexity, and so on. Instead of that, what do you think if I will just use the Fourier transform on that interval, on that window? Makes sense. Because Fourier transform, I don't need to change it. I don't need to estimate Rx in order to find eigenvectors. And also, I have a fast algorithm to find the FFT on that window, and log n. So the computational complexity will be lower. Whereas to find the eigenvectors of a matrix is high computational complexity. And also the representation using that, the coefficients, also it's high complexity. That's why window Fourier transform or short time Fourier transform is very useful to processing non-stationary signal, because it's much more efficient computationally instead of finding on each interval the Karun-Loew transform. But the reason behind it, okay, and the understanding is very similar. Okay? That's why we use short-time Fourier transform for many non-stationary signals. Or another transform, can be discrete cosine transform or other transform, because we want to sacrifice the performance by reducing the computational complexity using existing fast transforms. Okay. we can, in case that we have white noise, by the way, if we take white noise, then RV will be diagonal, like this. Why? Because any two samples of the vector V are uncorrelated, which means that this matrix is diagonal. So in this case, the MVDR reduces to this expression. It's just a special case. What we see here, so you can think that because that the MVDR filter reduces less noise, maybe it also the output SNR can be, in some cases, lower than input SNR. But actually, I can convince you that this is very easy to prove. Why do you think it's easy to prove? This is very easy to prove. Even by intuition, what do you think? How do I know that the output SNR with the MVDR filter is always larger than the input SNR? It's much easier than the other filters. Why? Don't be shy. Okay. What? The estimate. It has two components, X and residual noise. X is the same. The noise will be smaller than the input. So this ratio, the variance of this ratio, is always smaller. This ratio is with the output, always the ratio will be higher than the input, or at least equal to the input SNR. So this is very easy. With the Wiener filter or the trade-off filter, it's not so obvious, because we reduce this, we have distortion and with noise reduction. But with the MVDR, we don't have distortion. So the portion of the part of the signal remains the same. And this becomes smaller. So the ratio becomes at least larger or not smaller. Okay? Even easier. So this is nice. So therefore, we have also this property also for the MVDR, which is nice. That's why I don't show proof, but because it's easy to show it. Okay? Very easy. What I said before, so it's straightforward. Example. Let's see this example. So suppose that the signal contains superposition of a few cosine functions like this. And the amplitude of each cosine is different amplitude and different frequency and different phase. Okay? By the way, because it's a cosine, if I take a certain length of the signal, the eigenvectors will be very similar, in general, very similar to the Fourier transform. Okay? Either Fourier transform or some representation. Of course, it's not the Fourier transform, because the Fourier transform is complex. It contains complex. But it will be very similar. If I take the eigenvectors are different cosine. If you take a matrix Rx of something like that, the eigenvectors will look like cosine vectors with different frequencies. Very similar. Not exactly, but very similar. But it's not like the Fourier transform. It may be like cosine transform. Because the eigenvectors are real. All values are real numbers. So if I take this signal, and it contains k frequencies, what do you think? How many eigenvectors do I need to represent such signal in the signal subspace? What? K? 1? K? Let's think about it. The phase here is random. So answer that we need k. It's a good answer, but it's not sufficient. What? 2 times k. Why? Exactly. We need the cosine and the sine. Or we need the cosine or the minus frequency or whatever. But in order to represent cosine something with a random phase, we need the cosine and the sine. So if we take any signal like this, so any vector of length L, we have L eigenvectors. L divided by 2, half of them are actually cosine of the frequencies, and half of them the sine of the frequencies. And then any signal of length L can be represented as summation of cosine and sine. So for each frequency, we need 2 eigenvectors from the cosine and the sine of those frequencies. So I agree. We need 2L eigenvectors. So the rank of this vector, if we take vector of length L samples, we need 2k eigenvectors to represent signal like this. Okay, and suppose that we have also here white Gaussian noise. So white Gaussian noise, we can compute Rx. First, we know that Rv is diagonal with sigma v squared, IL, and Rx from the model looks like this. These are the elements of Rx. And if you check, the rank of Rx will be 2k. And suppose what we can do is we take the eigenvectors with the positive eigenvalues, and we take these 2k eigenvectors, and then we can represent these any signal of x by these 2k eigenvectors. So suppose for certain, in this example, suppose that AK, all of them the same amplitude, 0.5, and the frequencies are different. Okay, you need to use different frequencies for any signal. So it's 0.05 multiplied with k, so multiplication of k by 0.05. So you need to check that for the largest k is still smaller than half. So Nyquist frequency, it is satisfied. The Nyquist is smaller than the Nyquist frequency, so we don't have any aliasing. And then we take L equals to 30, and we want to see how K, what is the effect of changing K and the noise reduction. How K, if we take the MVDR filter, what is the effect of K on the signal distortion? What? No effect, right? Why no effect? There's no effect. K doesn't change the distortion because the distortion is 0. MVDR, obviously, 0 distortion. So K doesn't affect the distortion, but it does affect the noise reduction. Because if K is larger, then the signal subspace increases. The signal subspace, the rank is 2K, so it increases. So it means that we have less noise to suppress. In frequencies, other frequencies, okay? Because it reduces noise where signal is not present. So we can see this. So in this, we see the gain in SNR as function of input SNR, the MSC, the noise reduction factor, and the distortion. So you see the distortion, this desired signal reduction factor is 0 dB. No distortion, no matter what is K. So we have here different plots for different K. K equals to 1, 2, 4, and 8. 1, 2, 4, 8. So we see that when we increase K from 1 to 2, or we further increase it to 4 or 8, if we increase Ka, what happens to the noise reduction factor? Decreases. So because we have less noise to suppress without distorting the signal. So K increases, noise reduction decreases. Distortion, no distortion. Doesn't affect distortion. What happened with the gain in SNR? The gain in SNR necessarily is decreased because X remains the same. We reduce less noise, so the output SNR decreases. What happens with the MSE? The mean squared error. So the mean squared error, it means that if we increase, we have less noise to decrease, the MSE increases. Because the MSE comes only from this part, from the residual noise. If we have more noise, the MSE increases. Any questions? Okay. So here we see a very nice observation, because we saw the expression for the MVDR filter. So it's very nice to see how the MVDR and the trade-off filters, how can we express them when we represent the signal using the eigenvectors of Rx. Okay, we can do that. We showed certain expressions for the Wiener filter and the trade-off filter, but we can also express them in this space, of the space that's spanned by the eigenvectors of Rx. So if we write them, we can express Wiener. By the way, it's very nice how to use that, Woodbury's identity and so on. So the derivation is also nice. For people that want to practice the mathematics, I recommend to follow these derivations. And I can also give you the solutions and how it's derived. But the result here, the Wiener filter, can be represented in this space using this. So what is the difference between Wiener filter and the MVDR? This part. You see this part. So if with the Wiener filter we didn't have this part, and then when we applied the MVDR, when we applied it to the vectors in Qx prime, which are the first eigenvectors, we didn't have any distortion. Here, we add this matrix, and because of that, application of the Wiener filter to the vectors in Qx prime will not reproduce these vectors. We will distort. It will be lower. So it will reduce the signal. So we will not get the original signal in this part. We will get something lower, which is exactly the Wiener filter. The Wiener filter, what it takes in the signal subspace, it suppresses the signal according to the signal-to-noise ratio. But it's very beautiful to see the relation. It's only this matrix. If we remove it, so it's actually the MVDR. What do you think now? If to put the trade-off filter, what do we need to do? I remind you, the trade-off is similar to the Wiener, but we need to change RV with mu RV. But you need to be careful, just like I said, if you have different expressions with subtraction and so on. So if you add here mu, like here, you add mu here, so you get the trade-off filter. Okay? So we see the relations between different methods, different filters. We can represent them using different eigenvectors. I think you deserve tea now, or shall to continue? Now it's the tea break? Okay, so we have 10 minutes, or 10 minutes, or 10 minutes, right? Something like that. Around 10 minutes, tea break, and then we will continue from here. We will see some examples. Now we saw that all of them increase, or at least do not decrease, the input SNR. So the output SNR is at least as large as the input SNR. Okay, which is nice. Now we can ask ourselves, okay, suppose that we want to have a filter that, what is the maximum output SNR that can be achieved using such a linear filter? Okay? So before we go to the mathematics behind it, let's think about the intuition about it, around it. Okay? Suppose that we have a desired signal that is contained within a certain subband, from 1 kilohertz to 2 kilohertz, just like the example I gave you before. So with the MVDR, what we know, we remove the noise up to 1 kilohertz, and above 2 kilohertz, we increase the output SNR. Now suppose that I want to increase the SNR even further. How can I do that? What will I do? I don't say anything about distortion. I allow distortion. What will I do? Okay, what will I do? Okay, let's think. Okay, we talk about discrete signal processing, right? So the frequency transform is discrete. So let's think about the frequencies between 1 kilohertz and 2 kilohertz, discrete frequencies. For each frequency, we have a certain signal-to-noise ratio. What will be the signal-to-noise ratio that is obtained in this frequency range? So for each frequency, we can measure the signal-to-noise ratio, right? Now suppose that I allow you to have some distortion, which means I remove all the components of the signals, all frequency, except one frequency. I keep only one frequency. Which single frequency I would like to keep? The maximum what? The maximum SNR. Good answer. The maximum SNR. Okay. Now suppose that I keep two components, two frequencies. Which ones will I keep? The two top SNRs. Okay. Very good. Next question. If I keep one component with the maximum SNR, or two components with the top signal-to-noise ratios, which one will have more distortion? The two components or one component? Two components, more distortion or less distortion? More distortion? Why? I keep two components. If I keep two components of the signal instead of one component, so with two components, I have more distortion or less distortion? Less distortion. the more components that I keep, less distortion in terms of distortion. If I keep all the components, no distortion at all. So the MVDR keeps all the components from 1 kilohertz to 2 kilohertz, all the components without touching them. So there is no distortion. Okay. Now go back. I keep one component with the highest SNR, or the two components with the top signal-to-noise ratio. Which one will produce higher signal-to-noise ratio? One or two? One. Good answer. Why? Why one component generates higher signal-to-noise ratio? What? I agree. One component? Exactly. Because think about that when I compute the output SNR with two components, so we have the highest SNR of one component, we have we have the SNR of the second component. So the combination of two components, the output SNR will be somewhere in between. So it will be lower than the component with the highest SNR. Very good, very good. Now, instead of Fourier transform, what will we do if we work with these eigenvectors? Okay, so instead of working with these eigenvectors that we present or diagonalize Rx, what will we do? We will work with eigenvectors of what? We will work with the eigenvectors. This is very nice. We will work with the eigenvectors of, instead of Rx, we will work with the eigenvectors of Rv minus 1 Rx. The eigenvectors of this matrix. Why? Because the eigenvalues of this matrix, what does it represent? Again? Exactly, exactly. So the eigenvalues of this matrix correspond to the signal-to-noise ratio in each component. So if we take the eigenvectors and eigenvalues, the eigenvalues are the signal-to-noise ratio in each component, and we can order them in a decreasing order, and then the output SNR, the filter, is simply the first component, one component. So we keep only the one component that is represented with the eigenvector of this matrix. That's it. Very intuitive, very simple. So when you come to signal processing, I try to give you some tips when you work on your research. Try to think intuitively what makes sense. Not only the mathematics. And then maybe you think about, maybe you make mistakes, it's fine. It's actually, when you make mistakes, it's even better, because then you understand, and then you go to the mathematics. You can check if the mathematics and your intuition correspond to each other, if you get the same derivation, same solution. If you get something different, then you can think, why did I think intuitively differently? And then you can check, maybe the mathematics is inaccurate, maybe my intuition, and then you combine these two things, and you can also, in signal processing, you can play with some simulations, some data, and also to verify the solutions and so on. So it's a good practice to work like that. That's why I start with the intuition. And you see, when I ask questions by question, question by question, you can reach a good solution. And if not, you can think, does it make sense? I can check. I told you, okay, suppose that's something like that. So it's just like taking a simple example to try to get to a solution. Okay, so how do I now let's go to the mathematics behind it. So the mathematics is also very simple. What do I need to do? I need to write the output SNR. I can find the output SNR. I can find a mathematical expression for the output SNR. Okay, so what is the output SNR? Is the expectation of this squared divided by the expectation of this squared. So the expectation of H transpose xt squared divided by the expectation of HT VT squared. Right? This is the output SNR. So I can write it as H transpose Rx H divided by H transpose RV H. Okay? From here to here. Now I can ask, what is H that maximizes this ratio? So this is called Rayleigh quotient. Okay. So it's so if we have a structure like this, it's possible to prove, and this is a nice assignment if you like. Prove that H that maximizes this ratio is the first eigenvector of this matrix. The eigenmatrix with the maximum eigenvalue. So if we take, suppose that we define the eigenvectors, let's call it T, so we don't mix it with Q. I don't, let's see if I, here, T. So let's call it T. So Ti, so let's take the first eigenvector. We don't need, by the way, when you find eigenvectors, there are some fast algorithms to find, for example, the first eigenvector, the eigenvector with the highest eigenvalue. Okay, so T1, this is the eigenvector with the highest eigenvalue. Let's call it lambda 1. Okay, so don't confuse it with this lambda. Okay, let's delete this part so we don't confuse it with the eigenvectors and eigenvalues of Rx. So this will be lambda 1 T1. Okay, so lambda 1 is the largest eigenvalue of this matrix. So any filter that is proportional to this vector, zeta, any scalar value that is here multiplied with this vector, maximizes this ratio. Very good. So the question is, how to choose this value, zeta? Zeta should be different than 0. It can be any number that is different than 0. And because it will cancel. You see, if I put here zeta, it will cancel. So any number that is different than 0 is legitimate value to put it here. It will maximize this ratio because it doesn't change this ratio. how to choose this zeta, how to choose this parameter, this value. Okay? So when I talk about, because this is a ratio, according to our mathematical model, and because we have a certain degree of freedom to choose this parameter, this value, it's like a gain function. So I can put here a large value, smaller value. How does it affect? So it doesn't affect the output SNR. So any number here, I can call it a filter that maximizes the SNR. Let's call it max. A filter that maximizes the SNR. So when I derive this filter, I have an additional degree of freedom. Now I want answers from you. We talked about components, right? So the MVDR, suppose that we have a signal that is contained from the subband from 1 kilohertz to 2 kilohertz. And now I take all these components from 1 kilohertz to 2 kilohertz, we obtain the MVDR. If I take only one component with a maximum signal-to-noise ratio, I get the filter that maximizes the MSR. So you suggest just to keep this component without any, don't touch it. Don't touch it. When I say don't touch it, what do I mean? That for that component, it will not distort this component, right? So I can find this filter, or to find this parameter that both maximizes the signal-to-noise ratio and does not distort the signal in this component. Okay? How to find this parameter that does not find? Okay, I will ask you, think about it. Or maybe I can ask you something else. I can ask, what is this parameter that minimizes the mean squared error in this component, or the mean squared error between the signal that is derived using this filter and the original signal. Okay? Is it the same? Okay? Is it the same? The mean squared error is composed of two terms. One is distortion, one is noise reduction. How much noise remains? Okay, so if I compute this parameter, I can compute it such that the mean squared error will be minimal using such a filter, and so on. Okay, so you can combine additional criteria, or at least one of the performance measures, the criterion that we showed before, a criterion, such that it combines. It not only maximizes the SNR, but we can choose this parameter based on additional requirement or constraint. Unless you don't care about this parameter. So just choose one or something like that. Choose any value. But when you have a degree of freedom, try to find this value which makes sense, which makes a better for your objective, your application. Because maybe your application, you want, under this constraint, you want to minimize the distortion or to minimize the mean squared error and so on. Okay? So mean squared error and distortion are different things. So I have an additional degree of freedom. So I know that the output SNR for Hmax is necessarily larger than the input SNR, and actually it will be larger than any other filter. Of course, it's better than in terms of output SNR or gain in SNR, it's better than the Wiener, trade-off, MVDR, everything, any filter that we choose. And the output SNR for H max, we know that it's the eigenvalue of RV minus 1 Rx. Let's continue. Okay, so you need to make sure, when I told you to choose a component with the highest SNR, suppose that I have a few components with the same top signal to noise ratio. So actually, if I choose a few, all these components with the maximum signal to noise ratio, I can take any superposition of them and I will have the same output SNR, the same maximum. So the filter, in case that I have a few components with the same top SNR, which means that I have a few eigenvectors of this matrix, I have a few eigenvectors with the same maximum eigenvalue. So it's multiple eigenvectors with the same eigenvalues. So if I have that, I can write the filter as a superposition of these eigenvectors. And I can choose these parameters based on another criterion that I choose. Okay? And the output SNR, of course, will be lambda 1. Okay. And now I see that the output SNR with H max, it's always the largest. So it's larger than the Wiener. You see, the MVDR, always it will produce the lowest output SNR. But if we compare, and the output SNR with the H max is always the largest. And now if we compare the Wiener and the trade-off, they are somewhere between. So the output SNR with the trade-off is lower than the output SNR of the Wiener if mu is smaller than 1. Why? Because with the trade-off, we will reduce less noise if mu is smaller than 1. If we reduce less noise, the output SNR will be smaller than the Wiener. If mu is larger than 1, we will reduce more noise. So the output SNR with the Wiener, so the output SNR with the trade-off will be larger than the output SNR of the Wiener. So you see how mu affects the output SNR of the trade-off filter. But of course, the max, by definition, it maximizes the SNR. That's why it's largest. And the MVDR, because we have the most hard constraints and the components of the signal subspace that are not distorted, it will induce the least amount of noise reduction. That's why the output SNR is the smallest. And here we have the list of the filters that we have. So you see the formula, and we see the relations, some of the relations. See? We gave additional expressions, but here, this is how it looks like. Let's see an example with the maximum SNR. Okay, so suppose again that we have here combination of cosine functions, and we have only 4. So the rank of x, the vector x of L sample, the rank will be not 4, 8, okay? I remind you that because the phase is random, so we need cosine and sine. So the eigenvectors will contain the cosine, 2 pi f k t, and the sine. And then with a random phase, for some examples of x, of the vector x, of L samples, if the phase it's random, Okay? So if it's 0, maybe we need only 4 components. Okay? But generally, if we want to represent any vector of length L that is like this, for any phase between 0 and 2 pi, generally, we need 8 components. Maybe for some vectors of h, maybe we need less, but not in the general case. Which means that if we take the matrix R, the correlation matrix of the vector x, its rank is 8. Okay, so we need 8. And then we can compute the input SNR. Suppose that also here we have white additive noise. The input SNR, we see it from here. This is the input SNR. Now, always when you work on example in this single channel signal enhancement, we need Rx and Rv, according to what we saw. So Rv is the same, is a diagonal because white Gaussian noise, very easy. Rx, we see it here, just like in the example we saw before. And the rank of Rx is 8. And suppose that we take a specific example with the amplitude 0.5, all the components 0.5, the amplitude, and the frequencies are like this, different frequencies. And the length L is 20 samples. So we use 20 samples of Y, of the measurement, to estimate the signal X. Now we need to choose zeta. So we have different options. Suppose that we want to find zeta, this parameter value, zeta, such that the mean squared error is minimal. So what do we need to do? We take the mean squared error that is obtained with this vector, with the parameter zeta. So if we put it inside, we see that this is the expression. You see, it's very easy to use it. We just take the mean squared error, we put H max here, zeta T1, and take the MSC, okay, minus 6, and so on. So it's very easy to show that this is the expression. So you see, this is quadratic form of the expression. So we can minimize this. We can find zeta that minimizes this quadratic form. Very easy. Or just take the derivative with respect to zeta, which is a scalar, and equate it to 0. So you get this value. Okay? And then we can call this filter with this value of zeta, the filter that maximizes the MSR, the signal to noise ratio, and minimizes the mean squared error. Okay, both. First, it maximizes the output SNR, and then minimizes the MSC with this variable. Okay. Is it the same as the opposite? Suppose that I want to find filter that minimizes the MSC and then maximizes the SNR. Is it the same as the filter that maximizes the SNR and then minimizes the MSC? Is it the same? No. Okay, it's not the same. We saw that the filter that minimizes the MSC is specific. We don't have any parameter over there. And then this is the output SNR that we get. Here with the filter that maximizes the SNR, we have a free parameters because it's a ratio. So we have a free parameter that we can choose. Okay, good. Now let's move on. Let's see what do we get here using this filter. So we have here gain in SNR, MSC, noise reduction factor and desired signal reduction factor for different filters. The blue line is H max. Is the filter that maximizes the output SNR and minimizes the MSE. Okay, the zeta is minimizes the MSE. The red one is the winner. The red one is the winner. This one, okay, let's go to the green first. The green is the MVDR. And the cyan, this light blue, cyan color, is for the trade-off filter with mu equals to 0.5, which is less than 1. Less than 1. Okay? So if we compare the noise reduction, first the output SNR, we see that the output SNR with H max is maximal. Of course, as expected. With the MVDR is minimal, as expected. And then if we have the Wiener, the red, the Wiener filter, and the trade-off filter, so the trade-off filter obtains less output SNR than the Wiener because mu is less than 1. If mu is less than 1, it means that we give less weight to the noise reduction. So we reduce less noise. If we reduce less noise, the output SNR is lower. That's why it's lower. And the same relations we have for the noise reduction. So the maximal noise reduction is with H max. The minimal is with MVDR. And then we have the Wiener. And then we have the trade-off, which reduces less noise because mu is less than 1. And this is related also to distortion. So if the noise reduction is maximal, also the distortion is maximal. See here, maximum distortion is with the H max. Minimal distortion, actually no distortion at all, is with MVDR, the green. The Wiener and trade-off are in between. And because mu is less than 1, it suppresses less noise, but also less distortion. What about the MSE? The MSE, the minimal is with the red. What is the red? The Wiener. Of course. No matter what you have, other filter, the MSE, mean squared error, is always the minimal using the Wiener. So it minimizes the contributions of both the error from the distortion and the error from the residual noise. That's why the red is minimal here in the MSE. Any questions here? Okay. Now let's continue. Let's continue. Suppose you see what happens here. This is the trade-off filter. You see, the light blue, the cyan. What happens with the noise reduction as a function of the input SNR? The noise reduction is not constant. Okay? So, do you remember that we talked about the trade-off? That we have two options to design the trade-off filter. One with a constant mu, like here, or we can change mu such that the noise reduction factor will be constant. Also possibility. So if we design, we can change mu such that the noise reduction will be constant. Remember that we defined, we formulate the problem of the trade-off either with a Lagrange multiplier with a certain constraint on the noise reduction, or the residual noise-based MSE, which is the same, or we can use a constant Lagrange multiplier. So here we use a constant Lagrange multiplier, therefore the noise reduction factor is not constant. So we can actually, what we do, but before we continue, okay, to that, You see here in this example, mu is larger than 1, so the noise reduction is larger. Noise reduction is larger, output SNR is larger, but then the distortion is also larger. Okay. Now we can derive, we can find numerically mu, this is mu. We can find mu, the parameter, such that the noise reduction factor will be constant. For example, 10 dB. So if we find mu as a function of input SNR such that the noise reduction is constant, you see that for input SNR lower than 3.61 minus 3.61, mu is smaller than 1. And for input SNR larger than this value, which I can obtain numerically, mu is larger than 1. This is mu in dB. Okay? So if we have a constraint or requirement that the noise reduction for the trade-off filter will be constant, for example 10 dB, what we get, this will, all the other lines are the same. Didn't change anything. I just changed this line of the trade-off filter. So we see that if we change mu as a function of the input SNR, such that the noise reduction factor is constant, 10 dB, you see that it's constant. Of course, because the design is with variable mu such that it will be constant. Very good. And we see that according to the previous one, in this area, if the input SNR is smaller than minus 3.61 in this area, mu is less than 1. That's why the noise reduction is smaller than the Wiener. But in input SNR larger than minus 3.61, mu is larger than 1. That's why the noise reduction is larger than the Wiener. So we have different regions where the trade-off filter reduces less noise, and here it reduces more noise. So this output SNR will have the same relation between the trade-off filter and the trade-off and the Wiener filter. In terms of noise reduction, we have a similar relation between, because when we reduce less noise than the Wiener filter, we have less distortion than the Wiener filter. And in this region, we have more distortion than the Wiener filter because we reduce more noise. And again, with MSE, always the Wiener always give us the minimal mean squared error. Any questions? Okay, very good. So we have now time to continue for the Fourier domain. Okay? What? Continue. Yes, so I continue. So we define the problem of single channel signal enhancement in the time domain. And I want to show you the method how to work in the frequency domain. So in the time domain, what we did, we wrote, this is the model, yt equals to xt plus vt. And then we said, let's take a portion of L samples from the measurement. We define yt. These are L samples from the measurement. And we tried to estimate a sample, the sample xt, from this, using this vector. And some information. The information is that we know the correlation between any two samples in this vector for Rx and Rv. This is in the time domain. Now, instead of working in the time domain, and this is a causal filter, we go to the Fourier transform domain. So using the Fourier transform, we write it as YF equals to XF plus VF. And now we try to estimate a single component of XF. We try to estimate it here from YF, from this component. We assume that we know this component. Okay, so my question is, do you think that in the Fourier transform we will obtain better performance, whatever the performance criteria? Do you suggest to work in the Fourier transform or in the time domain? Which one will, what are the advantages and disadvantages of working in each domain? I can try to find a filter like this, linear filter, by applying a linear filter to the measurements in the Fourier transform, or I can find an estimate of each sample separately instead of each frequency. This is discrete frequency, okay? Everything here is discrete. So instead of working in estimating sample by sample, I will estimate for each frequency component the signal of the desired signal, or estimate the samples using a linear filter like that. So let's think about advantages and disadvantages. Okay, time domain compared to frequency domain. So it will be advantages, disadvantages, whatever. And let's us think, when do we need to work in the time domain, when do we would like to work in the frequency domain, and how to work on that, and what are the assumptions. Okay. Any suggestions? Whatever you say, just mention the differences, and then we will think if it's advantage or disadvantage. And what type of information do we use? Not everybody at once, one by one. Okay? Computational complexity. Okay? This is very important, computational complexity. So, if we talk about computational complexity, what do you think? Which one will be higher? For what? The time will be higher. Okay, so maybe this is high. Let's think. Here, the computational complexity, we need to transform the signal. So here it will be less. Okay, so when we work in the Fourier transform domain, This is a very good comment. We don't take the signal from minus infinity to infinity. It's not practice to work. We work on windows. So we work with the short time Fourier transform. So we work on windows of the signals. And then in the frequency domain, we work on a certain length. So here also we can choose. Maybe this will be the window. We can take a window of length L. So here we have also the complexity of the transform. So we take this window of length L, we transform to the frequency, so we have FFT, and then in the FFT we use the filter, and then we transform back. Here we apply the filter directly in the time domain. So which one the complexity is higher and lower? So he said it's higher in the time domain. Okay? So the number, let's count the number of multiplications. So in the time domain, when we apply a filter on a length L, so it's a length L, how many multiplications we have? To find a sample here. One sample. For one sample, how many multiplications? L multiplications. And then we need to find all these L samples in this window. So we have L squared multiplications. Okay? In the frequency domain, so we take a window of length L, we move to the transform domain, to Fourier transform. How many multiplications? Not exactly. You know, L log L. L log with the base 2 of L. Okay? And then we multiply each component with a certain value. How many multiplications do we have? L. So we have L. In the time domain, we said we have L squared. In the Fourier transform, this is the transform, L log 2 L plus L plus the inverse transform. So it's of the order of this. Let's write it to 2. So we have. So if we compare, actually it's not exactly L log L, it's order of that. So if we compare this and this, which one is lower? Okay. If L is high, large, this is high complexity. If L is small, then this is better. Okay? Very good. Very good. We made some progress. So in terms of computational complexity, it depends on the length of the window, the length of the filter. If the filter is short, it's better to do it in the time domain. If the filter is long, it's better to do it in the frequency domain. Okay, so L, let's write it like here. Small L, large L. Very good. Let's continue. Additional criteria. Computational complexity is very good. Important. Because the differences. What additional differences do we have between these two methods? Time domain. What? It will be more sensitive. I agree. I will refine it, what you say. I agree. I agree. It means, and I will give opposite example to what you say. What you say that, actually, according to what I understand, correct me if I'm wrong, if I misunderstood you, you say that in the frequency domain, we can suppress more noise. Actually, what you mean, I agree, that you can separate the desired signal and the noise better because we have a better representation of the signal. In the time domain, it's more mixed because each sample contains noise and so on. Okay. The thing is, suppose that I take the signal like this, and during some time intervals, during some samples, I have only the desired. And in some time samples, I have only noise, maybe spikes of noise. Would you recommend to work in the time or in the frequency? In the time. Because if you have some samples of spike noise, so you want to suppress only those spikes of noise. And then the signal will not be distorted because maybe most of the samples are clean, no noise. And only some samples contain noise, very, very strong noise. So if you work in the frequency domain, actually these spikes smear up in all the frequencies. So they affect all the frequencies. So it's better to work in the time domain. But if you have noise components that actually are contained in some of the frequencies, or especially if the desired signal is well represented, most of the energy of the signal is condensed into a few frequencies, like what we saw before. It's like cosine, superposition of some cosine functions. Or like speech signal, it's there is sparse representation in the Fourier transform domain, in the STFT domain, because the signal is well represented by smaller number of basis functions in the Fourier transform. Okay? So if you have a better representation of the signal, or actually if you have a better separation between signal and noise in a certain representation, then it's better to represent it over there. So what we did in the time domain, actually, we used the Karunen-Loew transform. So the Karunen-Loew transform, why? Because we wanted to separate between the components of the signal and the components of the noise. And then we were able to separate or suppress more noise without distorting the signal, or distorting the signal with the least amount based on the eigenvalues of these components, either the Karunen-Loew transform or the eigenvectors that diagonalize RV minus 1 Rx, which is based on the signal to noise ratio. Okay? So another criterion will be better representation. Okay? So better representation. It will be depending. I would actually I prefer to call it instead of better representation, source separation. This is more relevant. Source separation. So we will choose either time or frequency depending on the type of signal and noise, because the noise comes from other sources. So we choose here or here, which one gives us better source separation. Okay, let's continue. What else? Source separation, computational complexity. What do you think else? What about causality? In the time domain, we look back, L sample. What about window Fourier transform or short time Fourier transform? What about causality in the Fourier transform? Do we have strict causality or not? So in the Fourier transform, can we look forward and future samples? Actually, we look and then we can estimate a window from this window. So we don't have strict causality in terms of samples. We have some causality in terms of windows, maybe. So the causality constraint is less strict in the Fourier transform than in the time domain. So we can use more information. So it's causality. So here it's more difficult because we use only past samples and so on. Here we can use future samples. Okay, what else? Okay, let's ask something like this. I want to give you something beyond that. What we said that using a linear filter, we estimate this component in the frequency f from the component yf. Can we estimate this component from more than one frequency? Maybe all frequency from the vector. I can define a vector y that contains all the frequencies and estimate x, f in a certain frequency. Maybe suppose that this is a certain frequency component, but I will use all the frequency components in y to estimate that component, just like what we did here. I estimate one sample from all samples. Does it make sense? Or maybe for linear filters like this, maybe there's no point to do that. What are the advantages and disadvantages? Does it make sense to do that? And if it makes sense, when? Under which circumstances? On what does it depend? Okay, when I use more information, when does it make sense? First, if this information is important. Second, if it's reliable. Okay. If I estimate single component from a few, so I can estimate, this is one option, ZF equals to some filter, GF, multiply with YF. Okay, multiplication. So I use the same if. Another option, too, is ZF summation over all frequencies, let's call it K, from 1 to K, all frequencies. GK, YK. So I have two options. Which one? So here I need to find only gain for each component. Here I find a filter. I can write it as G, depending how G transpose Y. Vector like this that contains all the frequencies. By the way, I can write without it like this. I can write it like this. So here I need to find separate gain for each component. Here I find a filter, a vector like this. So here it's simpler, right? It's simpler to apply, simpler to find gains like this. Here I need to find a vector. So the computational complexity here is higher. But does it make sense to use different frequency? We know that when we have a linear system, so input frequency, if we have a frequency at the input, it will affect the output at the same frequency, not another frequency. So does it make sense, something like that? To estimate the signal at a certain frequency from other frequencies. Does it make sense? So sometimes people think it doesn't make sense, right? Because if we have linear systems, we want to estimate a frequency component from the same frequency component. But actually, it depends on the signals. How does it depend on the signals? Here, I will need information about the correlations between any two components, any two different components. So suppose that the desired signal is such a way that when it exists, there is high correlation between a few frequency components. They come together with some correlation between them. Actually, for voiced speech like ah or the voiced component, there is correlation between the components based on the format. Okay, or anyway, if you're familiar with that, but it's also for other signals. Maybe there is some correlation between the frequency components in the vector X. So they are not independent. And so if I know this correlation or the correlation matrix, correlation between these components for the desired signal and the noise signal, then I will use it here. If I don't know the correlation between these components, I don't know this information, or it's difficult to obtain, so I will use something like that. So this is more common to use because it's very difficult to know what are the correlations between frequency components in the desired signal. So sometimes people think, linear system, I can assume that frequency components are independent, statistically independent. And then I can process each frequency component independently. So this is not true, because sometimes people mix notions. They mix between linear system and then mix between statistical features of the signals. It's completely different. Okay? Sometimes it's true because it depends how the signal was generated. But if a signal is generated, even using a linear system, but the frequency components are depend with each other and they have some correlation, it's better to work with something like that. By the way, where do we work with something like that? For example, existing methods for speech enhancement. With deep learning, they don't work like that. They don't even work like this because it's nonlinear filtering, nonlinear. But they use all the information in all frequencies. And then you can ask these people, or someone that works on deep learning speech enhancement, why do you need to process all the frequencies? Maybe you can work on each frequency independently, and it's much cheaper. Okay? And then the answer is, if you understand this, so it depends. If I can work in the short time Fourier transform domain, and then on each frequency beam, I will take multiple windows. So I have the samples along the time for each window. And I will work on each frequency independently, which means that I exploit the correlations between components in the time axis. But the frequency will be fixed. Okay? So for each, I use windows. For each window, I do the Fourier transform. I take a certain frequency and try to find a filter along the time, along the windows, the time axis, but for the same frequency. I neglect the correlations in the signals between different frequencies. But if I use like an image around it, I can use also the information, the correlation between frequencies. So it depends what kind of information is useful. The more information that you use, it increases the computational complexity because you need more reliable information. It's not useful to use more information when you don't have reliable estimation of that information. This is very important. That's why also with deep learning, if you use networks which contain more parameters, larger networks, so you need more data to train it, and this data should be more reliable, the estimation. Any questions? Oh, I went so far. But it's very important. So this is like when we go from the time domain to the frequency domain. After you understand the differences, we will talk about how to do it in the time domain. And for simplicity, we will work with gains only. We will not work with filters in the frequency domain. So we neglect the correlations between frequency components of the signal and the noise, which makes our life much simpler because we don't need to estimate this information. Because this information of the correlation, it's difficult. It means that we need data. So we will require more stationarity of the signal in order to estimate them, more data. And sometimes we want to deal with time-varying signals and statistics. So this will help us to do it more quickly. Any questions? Okay, so we will continue tomorrow with the frequency domain. I will write a quiz today, some questions, so I'll give it to you only on the time domain. Some questions with some options to just circle, choose an answer, and see you tomorrow.